What if one of the deepest, most complex mysteries in all of mathematics wasn't really about complex formulas at all, but about something as simple as a coin toss? Today, we are cracking open the Riemann hypothesis to find a surprising secret hidden in plain sight, a secret made of simple arithmetic. Okay, so let's just dive right in. The prime numbers. They look random, right? They seem to pop up without any real rhyme or reason. But for over 150 years, mathematicians have been convinced there's a hidden music to them, a secret rhythm described by the legendary Riemann hypothesis. Now, if you look this up, you're immediately thrown into this very strange and intimidating world of complex analysis. It's all about abstract functions and something called their zeros on a complex graph. It's a lot. But what if I told you there's another way to look at this? A way that doesn't require any of that? So let's let's leave that whole complex world behind for a second. I want to introduce you to a quirky little character from the world of basic arithmetic. It's called the Mobius function. This function, you'll see it written as the Greek letter mu, so mu of n, is super simple. You feed it any whole number n, and it spits out one of only three possible answers, -1, 0, or +1, and it all depends on the number's prime factors. So here's how it works. If a number has a repeated prime factor, like 4, which is 2 squared, or 12, which is 2 squared times 3, the function just gives you a 0. Easy. If the number is made of distinct prime factors, you count how many there are. So for a number like 6, that's 2 times 3, two distinct primes, so you get -1 squared, which is +1. For 30, that's 2 times 3 times 5, three distinct primes, so you get -1 cubed, which is -1. That's pretty much it. And when you look at the first few values, you see this sequence of ones, -1s and zeros. It looks pretty random, doesn't it? It's kind of like flipping a coin that sometimes lands on heads, sometimes tails, and every so often just lands on its edge. The real question, the million-dollar question, is there a pattern here? Do the plus ones and minus ones balance each other out over time? Well, to find out, we start adding them up. We create a new function called the Mertens function, m of x. It's nothing fancy, it's just a running tally. You just add up all the values of our Mobius function, mu of n, from 1 all the way up to some number x. The best way to think about this is like a random walk. Imagine you're standing at 0. Every time our Mobius function spits out a +1, you take a step forward. If it's a -1, you take a step back. And if it's 0, you just stay put. So the big question is, where does this walk end up? Does it wander off to infinity? Or do the steps forward and backward pretty much cancel out, keeping you close to where you started? Okay, so we have these two completely different ideas on the table. In one corner, we've got this super abstract world of complex analysis. And in the other, we have this simple, step-by-step random walk. How could they possibly be related? Well, this is where the story gets absolutely wild. I mean, really think about it. On the one hand, you have the Riemann hypothesis, this beast of a problem about the zeros of the zeta function, zeta of s. On the other hand, we have this plodding little random walk, m of x, built from simple prime factors. They just feel like they come from different universes. And then comes the shocker. The Riemann hypothesis, that deep, abstract, complex problem, is true if and only if our simple little random walk behaves in a very specific way. They are the exact same problem, just wearing different clothes. The grand mystery of the primes is secretly a question about how fast this simple sum can grow. It's an absolutely mind-blowing connection. So what on earth does that big O notation mean, that O of x to the 1/2 plus epsilon? Well, you can think of it as a mathematical speed limit. It's saying our random walk is incredibly well behaved. The positive and negative steps cancel each other out so perfectly that the sum, m of x, grows incredibly slowly. So slowly, in fact, that its path basically hugs the curve of the square root of x. So why is this specific growth rate, this particular speed limit, so incredibly important? Let's put this into perspective to see why it's such a profound idea. This table really lays it all out. A landmark achievement in math, the prime number theorem, is equivalent to saying our sum, m of x, grows slower than x itself, which is already amazing, right? But the Riemann hypothesis makes a claim that is just fantastically stronger. It says m of x grows much, much slower, almost as slow as the square root of x. This implies a level of order, a degree of cancellation in the primes that is almost unbelievable. It's the difference between good and as perfect as it can possibly be. Now, this stunning connection completely transformed the hunt for a proof. Suddenly, there was a new front in the war, a new battlefield based on simple arithmetic. And over a century ago, one brilliant mathematician thought he had already conquered it. Way back in 1885, a mathematician named Thomas Stieltjes wrote in a letter that he had proven an even stronger result. He claimed he'd proven that m of x was bounded by the square root of x, without even needing that little extra epsilon bit. If he was right, it would have been enough to prove the Riemann hypothesis then and there. But he never published the proof. He apparently set it aside hoping he could find an even simpler way to show it, and when he went back to it years later, he couldn't reconstruct his own argument. It's just this tantalizing mathematical ghost story. One of the greatest minds of his time was convinced the answer wasn't in some far-off abstract world, but right here, hidden in the simple behavior of mx. And that is the secret. This deep, profound equivalence transforms one of the most abstract problems in all of mathematics into a concrete question of arithmetic. We don't have to navigate the world of complex zeros. We just have to track a simple random walk. It really leaves you wondering, will the final proof come from some breathtakingly new complex theory? Or has the answer been hiding in plain sight, in simple addition and subtraction all along?